In our generation, there were not yet a lot of R books. And so we had to read introductory materials we found online. And David Smith, as you may know, has contributed to the introduction to R, the official introduction to R manual, which, of course, at that time, we were very avid to read. And in the contributed section of the documentation on CRAN, you could find a document by Yves Rossel, who also gave an introductory treatment of the R language at the time. Now, Yves has done many more things for the R community than working on documentation for our generation. He's a professor at the University of Ghent. He is our local Belgian speaker at the conference this year. At the Department of Data Analysis he works, Faculty of Psychology and Educational Sciences. And actually is quite an obvious choice as a keynote speaker. One of the questions David asked or mentioned with respect to the perception of R is, does it do all the things we do? And in the beginning, I don't think it did a lot of structural equation modeling, which, as you know, is one of the centerpieces of statistical modeling in the social sciences. And so if we have good functionality for structural equation modeling in the R community, that is to a large extent thanks to Yves. So I'd like to invite him to take the stage and learn us all about the community around structural equation modeling in R. Thank you.
Good morning. Good morning, everyone. I see my slides here, but they're not up there. I don't know if that is supposed to be like, oh, there they are. Shouldn't worry too much. Welcome in Belgium. I'm the local speaker. So that's probably why I'm here, I guess. I'm a bit nervous, but you know, if they ask you to be a keynote speaker, and especially for a conference like this one, I'm usually go to conferences on structural equation modeling or social science statistics, something like that. This is more like a computer language conference. So I was a bit unsure what to tell you. So what I did is I watched the videos of last year. And last year, the opening speaker was no one less than Rick Becker. And he had that wonderful talk on 40 years of S, right? So here I am today, very humble. I cannot give you a talk that spans like 4 decades yet. I almost had a title like 7 years of Lavin, but somehow that didn't feel right. It's a bit so. Because I imagined that most of you are not Lavin users, and I also will assume that most of you are not in the social sciences or in psychology for that matter. I will introduce myself a little bit, just in a few bullets. Usually I start with saying how to pronounce my name, but actually Tobias, because he's Flemish too, he already did a fine job. But just for the record, because many people wonder, how do you pronounce your name? Well, for once and for all, this is it. Listen well. It's Yves Rossel. See? That wasn't too hard. Yves Rossel. Yves is a French name, like an Yves Saint Laurent or Yves Montand. And Rossel is very Flemish, and that's what makes me Belgian, I guess. That's how we are. So what you should know about me is I'm a psychologist, an experimental psychologist by training. I did postdoc work and my PhD in mathematical psychology. I'm not a computer scientist, I'm not a professional programmer, I'm not even a statistician. I do work with statistics quite a lot. I'm actually one of those guys who, you start psychology when you are 18 and then after a while you think, God, I should have done something else, right? And then you wander off, and ever since I tried to become some sort of a statistician, and I guess I'm sort of halfway now. So I'm a professor in Ghent. I would like to stress that's actually a full-time job. Programming R is strictly speaking, not part of my job. It's like an after-hours thing that you do. It's like almost like a hobby. So my audience, I teach a lot, obviously. You can see some of my courses on the slides, psychometrics and repeated measures, multivariate statistics, things like that. My audience are typically psychology students, students in educational science, so social sciences, if you want, in general. And I've been advocating the use of R for I guess, almost 20 years now. And as you may know, in psychology and educational sciences, the main program they use for statistics, still today, I'm afraid, is SPSS. And I've been trying to get rid of SPSS for a long time, and it's very hard. And I will try to explain a few reasons for that during my talk. The reason I'm standing here, I guess, is not only because I'm in Belgium, but I also wrote just one package, at least one that I made public. And this talk is in a way the story of that package. I will first give you a bit of an introduction on what structural equation modeling is, really, very briefly. But it's really about that package, and it's not going to be a tutorial on that package of how great it is and so on. It's actually more a perspective on how is life as a package developer. We have 10,000 or more packages nowadays, but what we never hear is the story behind those packages, and that's the story I would like to bring to you today. Oh, these are my social media details, as you can see. Just a few words. Yeah, who has time for that, really? Just, you know, because I'm local, I can do that, right? Ghent University, 200 years this year. 200 years. It's not the oldest one. Not the oldest one in Belgium, that would be Leuven, the Catholic University of Leuven. Much older, but we are a state university, quite big. For those who are interested in rankings, you can see some of the rankings, pick your favorite one. We are more or less in the top 100, if you want. I always say Ghent is not the best university in the world, it's not the worst university in the world either. One of the best things about Ghent University is in Ghent. If you have some time for traveling, maybe you were planning to go to Bruges. Halfway, you get off the train and you just walk around the center of Ghent. You will be astonished, I promise you. It's really worth your visit. Any famous people in Ghent? Well, maybe a few Nobel Prize winners, but they're quite old nowadays. Some people that you may have heard of. But the one I want to mention today is Adolphe Quetelet. Not only because he was a Belgian and he got his PhD in Ghent. He was one of the first 3 people who got a PhD in Ghent. You may know him from the body mass index, which is a term that he invented. And the local people may be surprised that he founded and directed the Brussels Observatory. We call it the KMI. Those are the people who give us the daily weather report. But the main reason is he's actually the guy, and he's often forgotten, especially in literature on the history of statistics, especially if it's written by a British guy or an American guy. They usually overlook this small but really important Belgian guy. He's the guy who introduced statistics and more, like, say, the scientific way of studying in social sciences. So he wrote quite a lot of interesting books. One of them is L'Homme Moyen, he was French-speaking, where he said, well, the average man is just, you have many traits, and most of the traits are normally distributed, and if you take the mean, and you do that for all the traits, then you get the average man. That was quite an interesting concept at the time. So, all right. Back to my talk. I will start with a fairly brief, the briefest introduction to structural equation modeling you ever got. I'm hoping for like 10, maybe 50 minutes, and then I will give you the landscape of software, so to speak, for structural equation modeling. It's quite a big world, so lots of software packages. And then I will, of course, talk about my Laval package. And again, I will show you a little bit of syntax to just more for historical reasons than I will not explain how to use the package or something like that. That's something that you can find out yourself. But more, you know, how did it start? Why did I start at all? Was there a big plan at the beginning? And for those of you who actually are Lavaan users, they may be not here today, but maybe they're watching the stream later on, I'm going to reveal some things that actually I forgot myself, namely the origin of the is measured by operator, the equal sign and the tilde that is quite prominent in Lavaan syntax. Where did it come from? I will also talk about growing pains, and you know, preparing this presentation, I've been thinking quite a lot about the last question here. Why are we doing this? And why should I keep on doing that? And I have a quite interesting slide on that later on. And because, you know, it's custom, I will end with a last slide. Then we all know it's done, right? It's easy. All right. What is SEM? SEM is structural equation modeling. If you have never heard about it, that's because you're not in social sciences. In social sciences, it's considered like the ultimate golden standard for analyzing your data. It's actually it's often misused too, and people overuse it perhaps. It's a very flexible modeling framework, and that's why it's quite popular. It's a multivariate technique, and it's all about statistical modeling. So there's no prediction involved. It has nothing to do with big data or things that you will hear during this conference. It's really about science and statistics from a very academic perspective, so to speak, in the social sciences. So the idea of statistical modeling in general is we try to understand the world. And you do that by collecting data, and you have lots of variables, and you see structure, and you want to understand the structure. Where is the structure coming from? And one way to analyze that data is using structural equation. It's not the only way, of course, but it's quite a flexible way to attack the problem. Now, you start with a hypothesis about how do you think, what is your theory telling you? What is the data generating model? And then you try to see if your model fits the data. Well, that's true for all statistical models. But what sets structural equation modeling apart are three things that you should remember. First of all, at the heart of structural equation modeling are latent variables. Now, latent variables are just variables that you cannot observe directly. If you're in psychology, you take it for granted. We talk about things like depression, personality traits, intelligence, things that we, you know, traits of people, but we cannot observe it directly. There's no instrument to measure and get you a value. Oh, that guy here, depression, 70 out of 100. It doesn't work like that. So we have come up with all sorts of measurement instruments. They can be questionnaires, test batteries, all sorts of things that gives you multiple numbers typically, and together they try to capture that latent construct you are after, like depression or motivation or whatever. And doing, say, regression analysis with those latent variables, that's pretty much structural equation modeling. That's what it's really about. The second thing, but I will show you that later on a slide, is it also allows you for having indirect effects and cycles and more complicated things than what you would typically have in a regression. And a nice thing about structural equation modeling is we use diagrams. And let me show you diagrams. And I will assume that everyone knows univariate regression. And on the slide you can see, I could use a pointer, but this will be a bit difficult with having two. So this is my dependent variable, right? Y, and I have, say, 4 predictors, and they all influence Y. That's univariate regression for you. And you can have a formula if you want to. And what we need to understand here is that the square boxes are observed variables. They actually appear in your data frame. You have observed those. The circles are unobserved. That's like a residual term. That's anything else that you haven't measured that is also influencing that Y thing. We often think of it as the measurement error or some error term in general, but that's latent, not observed. So observed square, unobserved or latent in circle. That's a complicated diagram in a sense, lots of symbols, and there's a residual, and there's an intercept. I will typically use those simplified diagrams here on the right-hand side. And so I got rid of the intercept. It's always there in the back of your mind. There's always a residual there too. So you just, but if you would always have them on the diagrams get cluttered a little bit. So once you get the hang of those diagrams, it's easy to talk about other types of statistical models. And this is multivariate regression. Now we have more than one dependent variable. Actually, we have two here. And the thing about the term regression is what sets it apart from, say, structural equation modeling is in regression, you always have a very strict distinction between dependent variables on the one hand, the y's in the gray boxes, and independent or exogenous predictor variables, if you want, on the other hand. It's either on one side or the other. There's nothing in between. And it's always the case that all the predictors, they all influence the dependent variables. That's a typical regression point of view, so to speak. Now, in structural equation modeling, we take a different perspective. So what we have here is we have variables like y7 that is also, so to speak, a pure dependent variable. It only has incoming arrows. And y1 up to y4, they are the exogenous variables. They only have outgoing arrows. But the ones in the middle, y5 and y6, they have like a double status. On the one hand, they are dependent variables, so they have incoming arrows. But they are a predictor on their own, and they also influence other variables, right? And that gives you a very different approach. Just to give you one simple example from educational sciences, so suppose we have children in primary school. So my kids, for instance, are 9 and 10 years old. They go to primary school, and they need to start reading. And there's lots of studies on reading and why some students or some children read really well and others do not really read very well. And so the ultimate measure at the end is reading ability, and that's a score. And that's, we would like to increase that for as many children as we can. Y6 here is reading frequency. And of course, the more you read, the better you get, right? And Y5 is reading motivation. If you are highly motivated to read, if you really enjoy reading, then you will probably read a lot. And if you read a lot, then you get better, right? And so why do we plot it like that? Well, suppose as the government you want to improve reading ability in general. If, for the sake of my presentation, think that indeed this is reality, then you can see that there are two things we can work on. If you want to improve this one here, we can say, oh, they need to read more, so we can have something in place that they are forced to read more, say. Or you could say, well, if we can improve motivation, and there can be all sorts of things that we can do to increase the motivation, that may also work because it has an indirect effect on reading ability, right? So that type of reasoning with indirect effects, we call it system read thinking. It's quite an important way of thinking about the world. And this is an example from educational sciences, but you will find examples pretty much in every discipline nowadays. All right, the other big special case is back to the latent variables. If you want to measure, say, depression or neuroticism or any latent construct, then often we have scores, and they can be from test batteries, they can be from questionnaires, and they are constructed in such a way that they're all supposed to measure this latent variable here, say depression. And once we have those scores for any subject, what the factor analysis model does, and that has been used in psychology for more than 100 years now, is it can more or less extract the common information from those observed variables to extract what we call a latent variable. And that one, we can do that for several latent variables, and now we could, for instance, estimate the correlation between those two latent constructs. And if you combine latent variables with all its measurement instruments, with that path analysis idea that you can have indirect effects, then you get what we call full structural equation modeling. That's what we typically have. We have multiple latent variables, and we have indirect effects, and we call typically the regressions in the middle, we call that the structural part of the model, and the rest is the measurement part of the model. And so who is using structural equation modeling? Obviously psychologists and educational science. It used to be like that thing only used in social sciences. But I would say, the last decade, and in particular the last 5 years, you will see that structural equation modeling, or at least the thinking behind structural equation modeling, has been adopted by several fields. And one of the things I did just for fun was I looked at the citations of my Laverne package. Who is using my package anyway? Well, one way to look at that is who is citing my paper on that. And you would think that like 99% of the people are in the social sciences too, but it turns out that you have people from all different fields. So we have, oh, I'm sorry, that's too quick. You have medical sciences, neuroimaging, biology. Oh, it was fun to see that there were a couple of Nature papers on climate change and global warming, and they had that big fancy diagram in there. And at the end, of course, the ultimate outcome was global warming, but they had that big system of things, variables that were influencing each other. And in the end, they were using my package to fit the model. That was quite nice to see. So another reason why people use SAM nowadays is a bit awkward. It's because other classical statistics, like, say, univariate regression, or at least the way it's implemented in typical software, including R, is very strict in the sense that it can do the job in the simple case, but as soon as you want something else, you're lost. If you have missing data, sorry, we can't handle that. If you want robust standard errors, you need a different package, and so on and so on. So if you want equality constraints, something that we take for granted in structural equation modeling, it's very hard to find packages out there that give you the ability to estimate models where you impose all sorts of equality, let alone inequality constraints. Like, this parameter needs to be larger than that one, and that one needs to be larger than that one. It's quite hard to find software that does that. A few examples. This is the SAM version of the pair t-test. Well, if you got Statistics 101, you probably know what the pair t-test is. You have two measures, pre and post. So how happy are you now? How happy are you after my talk? Well, we can compare that. Happiness is something that is not easy to measure, so we need a measurement instrument for that. And we have a latent variable. We have a score for everyone before, we have a score for everyone after, and we can compare the means if you want. And that would be a typical application of structural equation modeling. If we have longitudinal data, so we measure things over time point 1, 2, 3, 4, we have time series. We can study how one variable influences the other over time. So this type of thinking is used all over the place in econometrics, in neuroimaging, where they try to map how one region in the brain is influencing another region in the brain over time. That's the type of models that you can use. Oh, this is a growth curve model. This is probably familiar to people who know something about mixed models. So the linear mixed model with random intercepts and random slopes turns out to be, in a way, at least in the balanced case, it's a special case of structural equation modeling. And the trick is what you need to understand is a latent variable and random effects are more or less the same thing. So this is a random intercept here now, and this is a random slope. And so we can use the same infrastructure to fit the same model. And this is a classic example. This is a typical structural equation model. This comes from Ken Bolland's book from 1989. And you will find it in any manual, any handbook on structural equation modeling. It's also in the Laverne package. If you follow one of my workshops, that's typically the example I will show you. It's the political democracy example, and the observations are countries here. And what they have measured is the level of industrialization for each country in the year 1960, and also the level of political democracy, how free, politically speaking, is. How they have measured that, that's another story. You can look it up in the Laverne manual pages. There's some explanation there. But by and large, we have three latent variables, and people who are interested in, is there an indirect effect or is it a direct effect, and so on and so on. So quite a famous example. So, to wrap it up, some, it's a very confirmatory way of dealing with statistics. You need a model first. And that's, for many people, a big shock. You need to sit down and think about the world first before you start testing things. So goodness of fit, does the model fit the data well, is really central in structural equation modeling. It's enormously flexible, perhaps too flexible. We can handle all sorts of strange data. And it turns out that many models, especially if you go for the larger, the more modern approaches to structural equation modeling, where we also have clustered and multi-level data, the so-called multi-level structural equation modeling framework, can handle pretty much anything. And it turns out that many more familiar statistical methods like the generalized linear mixed models, for instance, they're just a special case. Disadvantages, well, it's very flexible, so that's a bit dangerous. You also, and this is specifically for people who are in the social sciences, if you are using SPSS on a daily basis, and you want to use structural equation modeling because you think it's a good idea and you need it, then you are out of luck, because SPSS doesn't do it. And then you have to go elsewhere. That's a bit of that used to be a huge problem in our field. Even if you do have software that can do it, your models can be extremely complex, and communicating your model to the software, that's a tricky thing. And it's easy to make mistakes. Structural equation modeling is not perfect. So there's lots of things that we can criticize on. There's some things that we have underestimated and that needs more technical work and more attention. And my personal standpoint is especially that structural equation modeling is a bit of an isolated field. They probably, I mean, they have chosen to be isolated, I think. They have their own journal. They usually have pretty much their own conferences. It's always the same people in that field. And it's a bit disconnected from other branches in statistics. And I think that's something that we need to work on. All right, so what about software? Now that you know that structural equation modeling is a nice, huge, flexible thing, we want to use it. So what can we do? Well, there used to be 4 big packages. We call them the Big Four. And if there is one name that you should remember, albeit mainly for historical reasons, the first package that could actually do it was called useR. And that was already in the early 70s, which at the time was an amazing thing that they could do it. It was quite complicated. You needed, it's an iterative method if you want to do maximum likelihood estimation, so you needed an optimizer to do that. Optimizers were not really easy to find at the time. The one guy who actually did it at the time was Karl Jureska. He was in Uppsala in Sweden. And he is often considered to be the grandfather, so to speak, of structural equation modeling. Later on, we had other programs. So there was EQS in the mid-80s. We had AMOS, that was in the 90s. AMOS was a bit special because the early 90s, that's when the PC was common, and we had, well, Microsoft came along, and we had graphical interfaces. And in AMOS, you could actually draw your diagram, the boxes and the arrows and the circles. And that was a lot of fun, obviously. Then later on, M+ came along. And I would say today, it's still the dominant package, at least in the commercial world. It's, the other ones are slightly outdated, so to speak. Not lots of updates, but M+ is really, really updated on a regular basis. It's by far the most sophisticated package today. The other big players like SAS and Statistica, Systat, Stata, they all have their own specific module too. There used to be a small little program that was free as in beer, but it wasn't open source, called MX in the early 90s. That was incredibly powerful. And what about SPSS? That's actually an interesting question, because SPSS is the main program used in social sciences. Everybody was using SPSS, and still is today. Well, SPSS, what they did at the time, they bought Amos. Instead of developing its own product, they bought Amos. That's fine. And then they made, if you ask me, the terrible mistake of not incorporating it into SPSS. if they would have done that, I would probably not be standing here today, because we would have structural equation modeling within SPSS and everybody would be happy. But they didn't. There was probably some manager guy wearing a tie coming and saying, you know what, if we sell it as a separate product, we can probably make more profit, right? And that's what they did. So they still had, if you could buy SPSS, and if you want to do structural equation modeling, you still needed to buy a separate package as AMOS. Well, that didn't work. Many universities said, well, it's already too expensive to have one license for SPSS. Having a campus license for AMOS, it's too much. So later on, and that's a bit of a story I want to tell this audience, because as you can see for yourself, the corporate world has invaded our R conference. And as a lesson to those people who are working with academic software, SPSS was later bought by IBM, and I was just curious this week to see what happened to AMOS really after all those years. Actually, it still exists, and you can still buy it. So if you Google later on AMOS and IBM SPSS, you will find easily its website. And if you look at the website, it has nothing to do with, it says what it can do for your business. And if you want to find out what it actually can do for your business, then you need to download the white paper. Well, that is to say, you first need to fill in your email address and register, and then you can download the white paper, and then I gave up, basically. So, but the message here is, I looked at AMOS today, what it can do, and to be honest, it's a disaster. Development basically stopped at the moment when SPSS bought the product. There was no further technical advancements yet. They just bought a product and they freezed it. It's still exactly the same, more or less, maybe some bug fixes or something like that. It also looks nicer than before. But technically, they're decades behind. Nobody in the field is using AMOS anymore, except some marketing people or something like that, typically in a commercial setting. But in academics, it's a lost case. So think about that during the conference. All right, so what about non-commercial packages then? There's not so much. And 10 years ago or 20 years ago, there was nothing. So today, it's much better. First of all, I would like to mention GLAM. It's not an R package, I hope you forgive me. It's a Stata module, but it's so well done and so powerful that it's really a prime example of how packages should be written. It's fully open source, well documented, there's a big book. It's incredible what it can do. It's not easy to use, and well, you need Stata first, but still. In the R world, there are more or less, I hope I'm not leaving out an important package, but I think there are 4 packages that I should mention. There is the SAM package, that was the first one, written by John Fox. It's been around since 2001. Then there was OpenMX, which is a huge initiative. There's really a big team there. It's in the University of Virginia in the States. And I mentioned MX on the previous slide. It's the same group. So OpenMX is like MX reborn, so to speak. And they started from scratch, but with the same philosophy. It's a wonderful product. And it's also on CRAN nowadays. Then there is my package. We'll talk about that later on. And there's the Lava package, written by Klaus Holst. He's in Denmark. Slightly more oriented towards biostatistics, I would say. And then there are also interfaces between R and those commercial packages, especially EQS and M+ automation. That last one is really a blessing if you are using an R and you must use M+ for some reason. All right, so the Lavaan story. And so before I start my talk on Lavaan itself, we have 10,000 and more packages on CRAN. And I'm often jealous if I look at those packages, what they can do, because they do something new, right? it could be a new statistical method, some new algorithm, it's typically work from a PhD student, something new, and it's a small package, and that person also can dictate its own standards, because it's new anyway. There's no tradition, there's no expectations. You can write your function just the way you like it, and that's just the way it is. Imagine that you have to write a package for structural equation modeling, so you enter a world that has been around for 4 decades. Plenty of software packages around, plenty of standards, plenty of expectations. That's not so easy, I can tell you. So, where did it start? When I was at the Department of Data Analysis in the first years, I did quite a lot of consultancy. Not in the commercial sense, I mean talking to my colleagues in the psychology department and educational science. They came to me, so to speak, with their output of useR or EQS or M+. They tried to fit a model and it didn't work, and I tried to help them out, basically. So that's how I learned about structural equation modeling in the first place, because as you remember, I do not come from that field. I'm a mathematical psychologist, so to speak. So I learned about that from an applied perspective. And I learned about the software too, because everybody else was using different software. Right? And most of the people were not using the full sum framework with the regression and all that. They were just using CFA, confirmatory factor analysis. Only the measurement part was what they typically did. And so I tried to fit models for them, one day using useR, the other day using M+, the next day EQS and so on. It was really complicated and repetitive, and being an R user, it was very hard to script all that, because you had to talk to external packages. Some of them only ran on Windows. I'm a Linux user, by the way, so that was a bit annoying. And I really wanted to have something in R, and the only thing we had in R at the time was the SAM package, which was better than nothing, but so many things that it couldn't do at the time. I needed missing data handling, I needed multiple groups, I need to be able to deal with non-normal continuous data. I wanted to have that Satora-Bantle correction in there, because that's what everybody wanted, and that was not available at the time. So the initial plan was to create a very small, private, not a public, private package, or just not even a package, I guess, just a bunch of functions in files that would do one thing, CFA. That seemed like a modest thing that I could handle, right? And I'm very much coming from the Unix tradition. That's why I'm using Linux, I guess. And in the Unix tradition, as you know, a small tool, do one thing, do it well. That's exactly how I felt about it. And I also had to teach, so I felt, if I have that package, I could actually use it for teaching too, so that would be nice. So I created the package around March 2009, never published, never got on CRAN. It was called CFA 2000. And the reason for the 2000 thing was, in my generation, I'm born in the early 70s, we had those BMX 2000 bikes. They were the best. Everything that had a 2000 ring in it sounded like something from the future, right? So CFA 2000 sounded like an awesome name, right? Oh well. This is how it looks like. This may be uninteresting for most of you, but for people who actually have used Lavaan before, and knowing how the syntax looks like today, this is how it looked like, well, more than 7 years ago. And okay, well, you had to specify a measurement model. So in the measurement model, we have 3 latent variables, and they are connected to indicators, as we call them. And this is the way I specified it. So it's a list, 3 elements, and the visual latent variable has 3 indicators. It's just a vector of strings. Okay, that seemed to work. That was not too bad, and that's what I did. But, if you do that for hundreds of variables, I didn't like the double quotes, lots of commas, so I tried to simplify that a little bit. And this is the next, This is the only slide with output, just for historical reasons. I'm showing this because people who are using a modern version of Lavaan will be surprised that it looks very similar. It's not identical. Things have changed a little bit, but still, by and large, it has that same feeling, so to speak. That's the next generation of syntax. I discovered that if you just, at the prompt in R, if you type visual equals and then you have a tilde, then R thinks you are specifying a formula, and you assign it to the visual variable here. And you can, that's nice. We don't need the quotes anymore, right? And, well, you can say, well, my measurement model is still a list of those guys, and that worked reasonably well. And later on, I came up with a fit measures function. It still had that dot here. Nowadays, it's forbidden, right? The dot. Now it's fits capital measures nowadays, but yeah, it's still the same function. And that worked for a while. I was quite happy with that. I probably should have stopped there, I think. But before you know it, there's then that guy who comes in and he wants to fit exactly that model, but there's an exogenous covariate there, age or gender, that influences those latent variables. We call it a mimic model in SAMWorld. And it turns out if you want to fit that model, you need a full sum package after all. So, well, after a while, it turned out to be a small step to go from CFI to SAM. And I created a package that was not called Lavaan, it was called SAM+. And I found the original description, not published. That was a private package in September 2009. And this is how it looked like. So this is that famous example, the political democracy example that we have seen before. And you can see more or less how we specified it. We have the same measurement models here. So it's a list of elements where I use that silly, strange symbol. You assign it to a formula, so to speak. But the way you should think about it is that the equal sign and the tilde, think of it as an operator. And it's saying, well, the latent variable int 60 is measured by those indicators. That's how you should think about it. And that's the measurement model. I had correlated arrows. They are the double-headed arrows here. This is the structural part. They are just equations. That's easy. So many parts, and they all go together in different arguments. That was one attempt. I wasn't quite pleased with that, because after a while you get too many parts. And so I figured I can do all of that in one big syntax, one list. That was already much neater. So it's a list. So those are all elements. And I'm a bit misusing the fact that you can use the tilde as a formula expression. And I was quite happy with that, but the users were not happy with that for the simple reason that you had to add a comma after each line, because we needed to have separate elements in the list. And so many commas were forgotten, and of course then it didn't work. So from a user perspective, this was not really good. And finally, I decided to make it a literal string. So you add a single quote at the beginning, single quote at the end. The reason why it's single quote is that I used to have lots of double quotes in the middle. That's why we have single quotes. And therefore, now it looks clean and easy, and that's exactly what I wanted. And the other thing was, before I was exploiting the fact that R could interpret expressions and understand formulas and what is the left-hand side and the right-hand side and so on. Now I'm lost, because this is just characters, right? So now I need to parse the syntax myself. That's the price to pay, but that allowed me to bring in labels and all sorts of operators, things that you cannot legally do in R, but I can do anything I want in my syntax, right? And that is how the Lavaan universe basically looks like. So if you are a Lavaan user, in a way, all you need to do, so think of SPSS people who are a bit scared of typing anyway, they need to be able to read in data. Once they have the data, they need to learn how to specify that model. That's the thing between the quotes. And then they need to learn how to fit the model and get summary or any information. That's all. You know. And that turned out to be a reasonably solution for many of them. And I think that's the reason why it somewhat became popular in the social sciences, because many people felt giving the diagram, seeing what you have to learn is just specifying that model in the syntax. If you can do that, you can run your model and you can actually use R, even if you're scared to do so. Oh, a little thing. SAM Plus was the name. The reason was we had the SAM package at the time, and I felt, well, it can do a bit more than the SAM package. So SAM Plus seemed like one reasonable name for it. And it also contained the name M+, right? It's a bit like Linux, sounds a bit like Unix, things like that. I think it's quite common in the open source world. I also contacted the M+ people quite a lot, asking many questions about their package, just technical questions. How do I get that number? I think that number is wrong. Can you explain me why? Things like that. At some point, I got an email back saying, literally, we own the M+ trademark, which is true. Using the name SAM+ can be construed as a trademark infringement. Oh, that's corporate business for you. They have lawyers for that, I guess. So what should I do? Should I make a fight? My legal department in the university, they were really eager to fight. That's what they do, those guys. They would love to make a case of that. But in the end, I know, it would probably bring all sorts of negative attention. I didn't want, and I must say, I respect those people. They created a wonderful package. And the guy who is running it, basically, he used to be a scientist. He made many useful contributions to the literature. So out of respect, basically, I'd say, no, that's not fine. And I changed the name later on to Lavan. That's the current name. Oh, that's the other name you should pronounce properly today. It's not Lavan or whatever the Texan guys make of it. It's Lavan. Can we do that once? Lavan? After a couple of beers, it goes better, I promise you. So Lavan stands for latent variable analysis, in case you wonder. Yeah. But all of that was under the radar, right? I didn't really have a plan to make that public and to maintain a package. You know, I have another job. But for some reason, I was a bit annoyed by that thing, and that's why eventually I decided to make it public anyway, that Lavan package. Not expecting much from it, but at least I was public. So Lavan was released on CRAN on, well, May 2010. And I gave a presentation at a conference like this one, useR, in the States, 2010. And from that moment on, my life changed quite a lot, I think. So people started using the package, which was a bit unexpected. If people start using your package, at first, that's great, right? It's really good for your ego, but it's only good for 5 minutes, and then you realize, oh, I have responsibility now. Yeah, and that's still a burden. And the bigger the group, the larger, at least, you feel that you have a lot of responsibility towards those users. And users, that's what users are. They always want more features, right? I would like to have this. I would like to have that. Could you add this thing? Oh, yeah, well. So more and more features were added gradually, very slowly. Some people are really angry that I go so slow, and that's why I need to remind them every now and then. I actually have a day job. Did I mention I have a day job? So I cannot work on Lavan full time. The world seems to think I do, but I can't, even if I wanted to. So huge improvements were made to the program. At some point, version 0.5, that's now 4 or 5 years ago, I switched from handling only continuous data, which was pretty much easy in respect to also handling categorical data. It was a huge step in the sense that you realize that the whole design of your program was wrong, right, to begin with. So you need to redo all of that, and that goes slowly because you cannot break packages and so on. It's really difficult to refactor your own software once it's out there, and I'm still struggling with that. It's really, really painful. But over the time, I mean, I'm a psychologist. What do I know about programming, not a lot, so to speak. I had to learn about things like optimization. There was an optimizer in there that every now and then failed. Why? Well, I had to study that in quite some detail and try to find solutions for that. So gradually, I understood that statistical software, there is more to it than just an interface. You need to pay attention to numerical aspects of that. And so for me, that was a new field. I had to learn and study about all sorts of things to make my program a bit stable and so that it wouldn't blink every time you throw at it a matrix that is, say, not positive definite. We could just stop with an error and say, oh, not positive definite, sorry. Or you could try to make the best of it. And it also forces you to make so many decisions. Like, for instance, what about negative variances? That's one of the things I've been thinking about quite a lot. Should we allow them, or should we re-parameterize the model so that you can never see them and so on? Well, some people may know that Laverne is one of the few programs where you can actually see negative variances once in a while. That's not a mistake, it's by design. But one of the biggest hurdles, especially at the beginning, time is moving fast, is I got results that were, in my opinion, correct, and I've checked and double-checked them, and I think they were okay. But what people typically do, imagine that you are an M+ user, and there's somebody telling you, oh, I have this free software, it does exactly the same thing as M+, but it's for free. Okay, let's try it out. And so you have your data, you have already run the M+ program, you have the output, you do exactly the same with Laverne, and then of course what do? You start comparing the numbers, right, one by one. And one of the things that was a bit annoying was some of the numbers were slightly off, not spot on. Well, if you know something about statistics and optimization things, it's nothing to worry about usually. But for many users in the social sciences, for them, it was really worrisome. Their supervisor didn't trust that. There's something suspicious was there. So one little example was, there was that statistic that we often use in structural equation modeling. It's the goodness of test statistic as a chi-square test statistic. And if you have non-normal data, but still continuous data, it's a bit skewed, then the test statistic gets inflated. And to correct for that, there's something called the Satoru-Bentler scaled test statistic. Quite popular because it will undo, so to speak, the effect of non-normality, and it will also give you a better fit of the model. So that's also why it's very popular. Now, if you run 4 different programs and you feed in exactly the same model, exactly the same data, you get 4 different numbers. And that was a bit of a problem. And none of them actually matched the Laverne. So everybody in the first year said, well, you know, good work, son. But, yeah, the Americans, they do that, son. Good work, really well done. But it's not quite right, is it? It's a tiny thing. So I will keep using my trusted M+ or EQS, and I pay $1,000 for that program, so it must be good, right? So I eventually came up with the mimic function. Yeah, that was really needed. So you can run Laverne, mimic M+, and then you get mimic results. I didn't want to do that, but I had to do that just because people would not take me seriously, really. And so I spent a ridiculous amount of time trying to figure out what those programs were doing. Because, of course, there's no technical documentation. It's closed source. It's commercial. We can't know what they do. And often, there was a very good explanation. By the way, I asked those people, and they never told me what they do. That's the corporate world. Once it's closed. It's a secret. So I tried to somehow come up with what are the little mistakes they might have made, or things that they have done differently. And it's, you feel like a private investigator. You try to find what is it that they do that systematically gives you that result. Many years of my life and many gray hairs there are due to that search. I'm still doing that. Every time I have a new feature, I'm confronted with that aspect of. So, the computer scientists tell me that what I'm doing actually is called software archaeology. I never heard about it. It's a nice term, isn't it? Trying to figure out, it's not only the current software, I also want to figure out what old software is doing because they seem to change over time. Is there a reason for that? What changed? Can we understand why? I learned an enormous lot of stuff, and I'm still processing the data almost literally. I want to say that the more you study, especially the older programs, and if you are lucky and you find some old manuals where they sometimes reveal some tricks they have used, I discovered something that I'm calling now the lost art of coding numerical software. Back in the 60s, 70s, 80s, people paid a lot of attention to details. Things had to be stable, memory efficient and all that. And if you have any algorithm that needed to do something, you would really need to sit down and think, what is the most efficient way to do it? Nowadays, because things are fast, we just do the textbook formula, and it usually works eventually. And if it's slow, then we say, oh, well, we will use C++ for that thing. And then we stop thinking, which is, I think, not a good idea. We need to go back and reinvent and re-document, because it's very hard to find that. There's no book on that, so to speak. All pieces and things. Maybe when I'm retired, perhaps, I will try to collect all that information about that. The lost art of numerical software. So Lavaan today, it's a big program nowadays. I think it's a big program. There's a website if you want to learn more. There's a paper in the nice Journal of Statistical Software. There's a GitHub thing, there's a discussion group. And the question I often get is, how many people use Lavaan now? Well, honestly, I don't know. How could I? How could I know? It seems like a lot, given that I get quite a lot of questions and so on. The only objective things that I can give you that are at least verifiable are, well, some people are so kind to actually cite the paper. Not everybody does, but so I have, since 2012, about 1,000-something citations. Hooray. The discussion group has 1,500 registered members, but you only need to register if you actually want to post. There are quite a lot of people who just read it. I don't know, downloads. There's that CRAN logs thing that you can look at. So I made a plot. This is just using basic plot stuff in R. It's quite useful, actually. There's an increasing trend. That's all I can tell you. I'm enough of a statistician to do not pay too much attention to whatever is on the y-axis. I mean, 15,000 people downloading that thing each month. Is there some sort of a click farm going on? Who are those people anyway? I don't trust those numbers, but I guess the trend is probably true. There's a whole ecosystem now. That's one of the nice things about the R. So a few packages I like to show you just very quickly to give you an idea. Packages that either build on or extend missing functionality in Lavaan. I'm especially proud of Blavaan, because it has the best name ever, right? For Bayesian latent variable analysis. And it's currently basically some sort of an interface for the JAX package. All right, a few others. There are quite a few, about 40 something. And so, growing pains. So this is a bit, that was the good news, so to speak. Lots of people use the package, but so for me, maintaining that package is often a bit of a burden. I spent more time testing, quality testing, all sorts of testing. I learned a lot about software testing. I didn't know what unit testing was 10 years ago at all. Now I do. Updating your package, that's a very nervous thing. That's a very dangerous thing. Because as you probably all know, you shall not break a package that depends on your package. That seems like very logical from a CRAN point of view. For me, it's a nightmare, because those packages, they often do things they shouldn't, like accessing internal slots, while there's a perfectly fine extractor function for it, but they access that internal slot anyway. And if I change that slot name or move it to a different direction, internally, of course, it breaks that package. So every time you have to contact those authors, please change it. And you have two groups, obviously. You have the ones who are responsive and the ones who are not. And if they are not, then what to do with that? Oh, that's really not easy. Users are quite conservative too. If you change something in the output, lots of questions and lots of complaints. So you feel like you're a bit stuck. Eh? The early days were quite adventurous. You could change, you could experiment, you could do all sorts of crazy stuff, and you could move forward really fast. Nowadays, I go very slowly, because every move I make, there's tons of people criticizing and say, oh, don't do that, don't, ooh. So it's a very emotional thing nowadays. Well, and of course, you shall not make any mistakes. I'm supposed to be a god. I'm perfect. I do not make any programming mistakes. That's what people expect. Unfortunately, it turns out I'm human after all. So, but for some reason, if you have a good quality package, then users literally expect that everything works perfectly all the time. And if you somehow drop the ball, then all hell breaks loose. Fortunately, that hasn't happened too much, but it's a nightmare. You think it might happen one day. All right, so maybe this is my last slide. I'm already 2 minutes late. Oh no, I have 1 minute here. So why do we do this at all? I often think I should stop. This is too much. For starters, this may surprise some of you, there's absolutely no funding. There's no big team. There's no Laverne team. It's a one-man show. It's basically just me. There's no support at the faculty level. My dean is not happy with this. He has told me a couple of times that I should not waste my time writing software that I give away for free. He doesn't understand the concept. He doesn't like it, because I'm supposed to do what most academics need to do nowadays, is just sit down and write papers. That's all we need to do. Even the university is not happy, because they have that thing they want to valorize. And they come to me and say, oh, you have an interesting thing. Maybe we can make money with that. And then I have to explain to them the whole concept of open source, which for them is a bit of a shocker. Also, users, people who use your package, 1999, the majority is nice and grateful, but there's some of those people who will email you and shout at you and say, oh, you wasted my afternoon because it didn't work, you lousy programmer, or whatever. It can sometimes be, well, not so nice. Why continue then? Well, it's a learning process. I'm an academic. I'm eager to learn. I have learned wonderful things that I probably would never look at if I wouldn't do this. So I know things now about numerical techniques that even civil engineers have never heard of. I learn new things about statistics, because I actually know how things work in a program. I learn about mathematics, and of course, I think I know the field of structural equation modeling from the inside out, so to speak. It feels more useful than writing yet another paper, at least to me. You meet interesting people in conferences like this. You get invited everywhere. You give workshops, and that's quite nice. And I honestly believe that the main thing for the academic world is that finally we have software that is open source. Like the M+, for instance, is brilliant software, but it's a black box. We don't know how they do it. And so how can a field proceed if they don't even know how things are computed? And that's why we need to change it. But will I do that for the rest of my time? I don't think so. So at some point, eventually, when I feel somehow that my work is done, I will give it to the community, and then somebody else has to take over. I will stop here. Thank you very much.
Thank you very much, Yves. I have learned a lot through the lens of Lavan, and I think many of us have done. There is time for one question. Yeah, I must admit I don't see from. Okay, we have someone there in the back.
I'm sorry, can someone relay that question? Or can you come to the front, perhaps? Say again? The most interesting outcome that I've seen in an application, you mean? Huh. There are thousands of applications, so... Wow. You get one question, it's a difficult one. Never thought of that. So, I honestly don't know. I'm not, I'm not an applied user, so I'm always intrigued by all the questions that people ask in all those fields. And I'm also intrigued by the way they think and how they apply statistical models. The results they get from that, I'm not particularly interested in that. So I usually do not pay attention when they tell me, so I'm afraid I have no answer there.